Hello, everybody, and welcome to another Hubble Hangout. This week we've got another great hangout planned for you. My name is Tony Darnell. I work at the Space Telescope Science Institute, and astronomers using the Hubble Space Telescope have looked at the Andromeda galaxy, and they have found a halo. Not just any halo, but a giant halo, and we're going to talk about it, what that is, what it looks like, and how they did it in just a little bit. But before I get started, I have some announcements to make. I have a lot of announcements this week because there's a lot going on, as you probably already know, and if you care about dwarf planets, which I guess a lot of people do, then you are going to be in for a lot of fun this month because it is Pluto month. The New Horizons spacecraft is on its way, and next week will be the big week. July 14th is the scheduled day, and if you care about looking at and following all of the things, my best advice to you would be just to watch NASA TV, because all week long they're going to be doing things with New Horizons and things like that. Also, this is NASA's Small Worlds Week, and if you are interested in all kinds of different things having to do with small worlds, then tomorrow, starting at noon Eastern Time, they're going to have a series of Q&As. They're going to be looking at dwarf planets late in the afternoon. They're also going to be looking at having discussions on comets, like was it possible that life was brought to Earth from another comet? They're also going to be looking at asteroids. There are going to be Q&As on asteroids? Is there a possibility for any of them hitting us, for example? Things like that. So this is NASA's Small World Week, and I think there we go. She's cycling through them now. There's the one on asteroids. That's at 1 o'clock Eastern Time. And the way you get there is you go to sunearthday.nasa.gov. I've got the link in the description box below. So that's when all of them will be. And I think these are just audio only. There's the one on comets. Could comets have brought life to Earth? That one's the first one. That starts at noon, and then going all the way through 3 o'clock. So an afternoon of Q&A, and there's the dwarf planets one. What worlds lie beyond the giant gas giants? Oh, and this icy moon was good too. Do habitable worlds exist beyond Earth? So I highly recommend you check those out. If you've got any questions, you want to interact with scientists who think about these things all day long, then that is your chance. Tomorrow, Friday, July 10th, starting at noon Eastern Time and going all the way through to 3 o'clock Eastern Time with the last one. So there is, in addition to the Pluto stuff going on next week, I can't believe I'm saying this, but there is a thing you can do this month, folks. If you're a real fan of Pluto, and I mean a real fan of Pluto, you can start and host your own Pluto Palooza. That's right. There is a way to do that, and there's a link also to that in the description box. I guess this is done by the Johns Hopkins Applied Physics Lab. They've put together a bunch of materials to help you host your own Pluto Palooza. Are you going to do one, Scott? You can do it anytime this month.
We'll see how things turn out. It's very possible. I have many wonderful, nerdy, planetary friends out here in Pasadena, so I'm sure we can find something to do.
Okay, well, make sure you post about it on your Twitter account, and people will show up at your house.
It'll be up on Twitter and Instagram. It'll be everywhere.
I'll be honest, I'm not sure what you do at a Pluto Palooza, but there's a bunch of materials there to help you do whatever that is. Also, as I mentioned, coming up, there's a thing called Pluto Time, which is an app that NASA has developed that lets you simulate, or at least try to get a glimpse of what it's like on Pluto, both in the evening and morning hours. It'll calculate for you exactly where on the planet based on where you are on the planet, it will calculate what the sun would look like from Pluto at that particular time. So it's called Pluto Time, and there's also a link to that. So and finally, they have videos every day. They're broadcasting a new video on Pluto every day. The link to that is also in the description box. So it is going to be a Pluto extravaganza. I like that better than Palooza. This coming month. So by all means do it. In fact, it's so much so that I think we're going to be taking a bow out next week and letting all the Pluto events happen. So there won't be a hangout next week either.
Okay. Although, to be fair, I'm sure I will be tweeting from Hubble of our images of Pluto and celebrating and like, yay, go New Horizons.
Yeah, I've been following you on Instagram. You've been doing a lot of things with Hubble too. You've been going different places with Hubble. I've been following you on Instagram. I've been watching you.
So I have a hashtag called Hubble in me. A few weeks ago, I went to the Endeavor exhibit here at the California Science Center, and I found this awesome little space shuttle that had a Hubble Space Telescope in it. So I hacked it and removed it, and I take it everywhere I go and take selfies.
Oh, you voided the warranty.
If you want to follow the hashtag Hubble and me, you will see the silliness that I get up to. My last one was when I was rock climbing and then had ramen afterwards. And
yeah, that actually looked pretty good. I wish there was a good ramen place near me. Okay, so all right, let's get to today's hangout. Speaking of hashtags and social media, we're going to tell you how you can interact with us during this hangout in just a minute. But let me welcome my good friend Carol Christian, who I don't know if you can adjust your camera a little, but you're being eaten by your lower third there. Hi, Carol. Dr. Carol Christian. She's the outreach scientist for the Hubble Space. There you go. Thank you. Welcome back. Hello. And also
I'm
joining
not
me.
back. I'm still here.
you're still here.
She never left. She's still part of the last hangout. She just stayed there and sat there. We forgot.
Absolutely. Absolutely.
Oh my gosh. All right, and Scott Lewis, he is our internet driver extraordinaire. Hi, Scott. Why don't you tell everybody watching how they can interact with us during this hangout? Because we want your questions and comments.
Absolutely. So, I mean, as sure many of you know, on Twitter, you might have seen us on Periscope earlier in our, I guess,
yay, Periscope people, that was fun.
And I'm sure we'll be incorporating more of that later on. But speaking of Twitter, you can engage with us on Twitter using the hashtag Hubble Hangout. Also, please follow us at Hubble Telescope, and I will be tweeting out pictures and stuff like that throughout this hangout. If you have questions for us, please use that hashtag because I will be able to see them and post them up here. Also, since we are broadcasting live on Google Plus and YouTube, you can interact with the Q&A app, which is on both of those. I just posted on Facebook as well into our event that we're live. You can click on the YouTube link, and it'll give you another option. Say, we're answering your questions. You can ask your questions. They can be upvoted by other members of the community, and when we see them, we can select them and answer them live on air. And then also just regular commenting. So you can comment on the YouTube page itself, on the Google Plus page, and I'll try to keep an eye as well on anything on our Facebook event as well. So all the internets are being watched, and please try to keep them in one place. It makes my job easier, but I will be an octopus and reach out everywhere.
Yes, we will try to capture you as much as we can. So Carol, somehow you got cloned. There's two of you.
Yeah, I did.
Okay.
I don't know what's going on.
All right, so let's get to the topic of today's hangout. As I mentioned earlier, scientists have been using Hubble for a variety of ways, and one of the ways in which they've been using it recently is they've been looking at the Andromeda galaxy, one of the nearest galaxies to us. It is a spiral galaxy much like our own. It's also heading straight for us. It's about 2.5 million light years away. And joining me to talk about their observations is Dr. Nicholas Lehner from Notre Dame or Notre Dame, whichever way you want to put it. Welcome, Nicholas. It's good to see you. Also with us, Chris Hoke also from Notre Dame. They are here both to discuss their observations. So, Nicholas, let me start with you. Why don't you tell us a little bit about these galactic halos? Before we get to your observations, I want to take a step back and say what are these things? Are these, when I think of halo, I'm obviously thinking of one that I always have over my head because I always have one of those. But what do you think about? Give us some idea of what these are, these halos.
Well, the halos that we are. Do you hear me? Yes.
Yep, loud and clear.
Yeah.
Yes. Sorry. So the halos that we're looking at are gaseous halos. That means it's gas. It's not these dark matter halos that we can look. So that's the first thing I would say. And they are basically, we think that they have been formed at the same time that galaxies, and they are completely part of this process of galaxy formation. And so the shape of these halos, they can be we think they are basically, they could be spherical around the galaxies, therefore their shapes are not very well constrained right now. So all the galaxies, we think that all the galaxies in the universe have halos.
Say that again. All the galaxies.
All the galaxies in the universe have some kind of halos, and
regardless of their type, regardless of what they are.
Regardless of the type, and they can be, and depending on the mass of a galaxy, these halos can also have different masses.
So we have one, the Milky Way then.
So the Milky Way is most likely one. We know that we actually have some evidence that the Milky Way has some halo. The problem living in the Milky Way is that we don't know, we can't really know its extent because we don't have background sources far away enough that tells us the scale of the Milky Way halo, which we can actually do with M31 and Andromeda. Sorry. So, yes. So basically, all galaxies have halos, but these halos are not static. So it's not. It's like galaxies; they are not static as the universe evolved or as the galaxy evolved. And we think there is an intimate connection between the evolution of the halos around galaxies and the host galaxies, and this intimate connection actually we think is driving the evolution of galaxies, and that's why we are so interested actually in understanding these huge gaseous halos of around galaxies.
Okay, so give us some idea. So what are the general characteristics of these halos? Are there any? Can they be categorized much like galaxies? Do they vary with the type of galaxy they're in, and are there specific wavelengths in which they're brighter to see than others?
No, so the gas that we're looking at is the gas span a wide range of temperature. So it goes from a few 10,000 Kelvin to very high, much higher, million degrees Kelvin. So it really depends on the wavelength that you're going to study the halos. So as far as we know, so we learn different things by looking at different wavelengths of the halos.
Okay.
But we cannot characterize yet the halos like we see, for example, spiral galaxies and elliptical galaxies. We don't have this type of categorization for the halos of galaxies. Therefore, we feel that they have different properties depending on the type of galaxies.
Okay, so and in this particular case, you guys were looking at the Andromeda galaxy. And by the way, I should mention that your results appeared in the May 10th edition of the Astrophysical Journal, for those of you who are wanting to read the paper itself. But you looked at the Andromeda galaxy, one of the nearest galaxies to us. So the nearest galaxies, I think, are the large and small Magellanic Clouds. Those are dwarf galaxies, and they're really close to the Milky Way. But this one, tell us a little bit about the Andromeda galaxy for those who may not know anything about it. We all know the name, and we know it's very bright in the sky.
But the Andromeda galaxies is, we think it's a twin of the Milky Way galaxies. It has about the same mass.
A twin of the Milky Way.
Yeah, in the sense that it has very similar masses. It has, we think also it has very similar radius, diameter. And they are both spiral galaxies. Therefore, Andromeda may be in the way of actually transitioning from a spiral galaxy to an elliptical galaxy. It's actually, we think it's in this what we call the green valley, which is a technical term.
I'm sorry, say that again. It's called the what?
We think that the galaxy is transitioning from this very active galaxy that forms stars to a more quiescent galaxy, where the star formation of the galaxy is much less, and that transition is called, we go through the green valley, but that's just technical. So,
wind barrier.
But the Andromeda is basically the closest massive galaxies to the Milky Way, and that's one of the reasons we targeted this, because it's also there that we have many background QSO to look actually and study this area.
Okay, Scott's got a picture up now of the Andromeda, but it doesn't look like most Andromeda galaxy pictures I've seen. What's up with this? What is that?
So, so the one that we're seeing here is it's a galaxy image. So it's only revealing really
galaxy image.
The hot stars and also where the hot stars. So it's a galaxy. It's in the ultraviolet wavelength. So it's in the similar wavelength that we actually did a study. But here we're just looking at the emission from the hot stars from the Milky Way. So
this is the Andromeda galaxy in the ultraviolet, and it shows the new stars that are being formed.
Yeah, so very hot stars, and in the center you can see at the resolution of galaxy you don't see the star, but it's all very active too, forming the stars. So, but it does show still the spiral arms of we can see the different spiral arms of Andromeda, and so it's this majestic spiral galaxy. And but clearly from these images, but one of the reasons I picked this is because it's the same UV wavefront, but you can't see anything really beyond the disk of Andromeda.
Right. So this study, in order to see the halo, because I don't see any halo here.
No, there's nothing.
This is you needed to use the ultraviolet wavelengths. Chris, let me get you in just a little bit on this discussion. Do you have anything you'd like to add about some of these observations of Andromeda?
Well, I'd just like to say, I mean, to follow up on something that Nicola was talking about, the halos are sort of so diffuse, so low density, that they're incredibly difficult to image at all. And in fact, we can't take images of them with current technologies. This is one of the future hopes, is that we can directly image these sorts of giant gaseous surroundings of galaxies. So we use a completely different technique, which is to look at the way in which the gas shadows the light from background objects.
Okay, good. Don't go there yet, because I think it's really cool the way you found these things. But and I want to go there. I do, but I'm not quite yet. So Nicholas said that these halos are hot, and you're saying they're diffuse. So are these just very tenuous, very well? First of all, maybe Nicholas, you should tell us what you mean by a hot gas, and then how can something? What are the temperatures, for example? And then I'll have Chris comment on how diffuse they are.
Sure. Well, the temperature that we probe with the Hubble observation is probably around 10,000 Kelvin. Or maybe a bit higher, depending.
Wow, so they're like star hot, right?
Yeah, or even hotter. I mean, some of the ions that we look may trace actually 100,000 Kelvin gas.
100,000 Kelvin for these.
Yes. So and Chris will answer, but that's why the gas is also very diffuse. But if we could observe it in X-rays, so much hotter gas, it will be. It's very likely that there is even million-degree gas in Andromeda, and that has been tentatively, and well, more than tentatively, but with Chandra and XMM observations. So these are X-ray space-based telescopes. They found X-ray hot gas around galaxies, halo of hot gas, but at very small.
You can see these halos in X-rays.
But the problem is at much smaller distances. We can only probe the inner region of this halo in X-rays, while with our observation we truly have probed the entire region of the halo of Andromeda.
Okay, so what about? Okay, so let's talk about how thin they are. What's the general density of these things, Chris?
If you want to think about the most basic building blocks of gas and stuff in the universe, it's hydrogen.
Right.
And so essentially, if you took a sampling of the gas in these halos, you would have about 1/10 of a hydrogen atom per every cubic centimeter.
Oh wow! So that is.
I'm sorry. I'm sorry. It's even worse than that. I messed that up. I was doing the conversion wrong. It's 1/10,000th of a hydrogen atom per cubic centimeter. So you need.
You know what? It's not going to matter. It's
but it doesn't matter. Because
I know that's orders of magnitude different, but the thing is, it is. You know, when it comes to visualizing it, I get it. I see what you mean. They're very thin. So that's you know what this reminds me of? It reminds me of when people talk about the solar corona, the atmosphere around the sun. They say that it's about 1 million to 2 million degrees, and it's also very they call it optically thin. And I guess maybe it's not as thin as these halos, but this is kind of like a corona of the galaxy, isn't it?
And in fact, that's another phrase we use to describe these so-called halos, is we call them coronae, especially if they're at that sort of 1 million degree type temperature. So that's a very apt parallel there. That yes, we call them coronae, although we're looking at the somewhat cooler gas that's probably embedded within that 1 million degree gas that's also there, but so far invisible.
Oh wow! So okay, getting back to the Andromeda galaxy, then what where would you categorize this as far as its temperature? Is it the 1,000,000 degree type? Is it more on 10,000 degrees? Or
well, so this is one of the interesting things about these halos is that they probably have a huge range of temperatures and densities represented. There's probably a lot of gas that's at 1,000,000 degrees. There's probably a lot of gas that's at 100,000 degrees, and a comparable amount that's at 10, 20, 30,000 degrees. So it's all over the map. And in part that's because of, well, in part we don't know why exactly it shows that huge range of temperatures, but it has to do with the different processes that feed the galactic halos.
Okay, so let's go to now I want to talk about the way in which you saw this halo, the way in which you found it. And in our press release, we had this schematic of the Hubble telescope looking at the Andromeda galaxy and its halo. Scott, can you put that up when you get a chance? And when he gets that up, maybe you can talk a little bit about, here it is, about how these observations were made. You said earlier that these were bright in the ultraviolet, and to see them, you needed to look at background objects, and you picked some really cool things. Why don't you talk about that, I guess, Nicholas?
Yes, so what we use is this background object of quasar, so they're very luminous galaxy at higher redshift. And we use them as the background source to eliminate the gas in the foreground. And in the way that so in this image, the way that we have selected these quasars, we selected them to try to probe a wide range of distances around the Andromeda galaxies to see the extent of the halo of Andromeda. And so we have some that goes at distance about 4 million light years, 2 million light years from Andromeda, some at within 1 million light years. And the neat thing that we could do with our experiment is truly show that we don't find halo gas beyond 2 million light years. And because we have nearly no detection beyond 1 million light years from Andromeda, so in radius, while within 1 million light years we have nearly 100% detection in absorption. That means some of the halo gas of Andromeda is removing some of this light of the quasars, and that's the signature that we actually detect the halo of Andromeda.
Right, and this is one of Anfield's awesome schematics. So I just want to go over what you're talking about a little bit better. So as the Hubble looks through the Andromeda galaxy, the way you see it is a small dip in brightness as the quasar, the light from the quasar passes through the halo. But but by using another quasar somewhere off in the distance, if you don't see that little dip, then there's no halo. And that's sort of how you're getting the boundary conditions of this 2 million light year diameter circle here. That's and so how many quasars did you look at?
So we had in this sample we had 18 quasars, and these were all selected because they were already in the archive of the Hubble Space Telescope.
Good old mass. Okay.
So they were used actually for other science purposes originally, but they were located in the general direction of Andromeda. And so we have 18 quasars, but if I remember correctly, there were only 5 quasars within the radius of 1 million light years, so in this inner circle that we see in this picture.
Yeah.
And that's
what blows me away is that there's that many quasars at all to use. Let's back up a little bit. We should talk about what a quasar is. Quasars are these very bright, almost some of the brightest objects in the universe, and they generally are the result of a feeding supermassive black hole. We've had many hangouts on these before, but I just want to remind people what a quasar is. They're quasi-stellar objects. They're extremely bright, and they are very bright in the high-energy wavelengths, which I guess you would need to be able to see these dips in brightness, correct?
Correct. Yeah.
So for one particle per 10,000 cubic whatevers, that seems to me like a pretty amazing thing. Are high energies required because the lower wavelengths, I think, would just go right through it, right? They wouldn't be affected at all. So infrared, for example. Am I right there?
Yes and no. It's more like what the diagnostic that we have actually to detect this gas is in this ultraviolet wavelength. When you go in the ultraviolet wavelength, you have all these atomic resonance and ionic resonance line, and they probe different gas phase, meaning different temperature of gas, and that's why we can actually detect it. So when you go and the gas that we know is typically hot, so yes, when you go to infrared, it will be much more difficult to detect it. We don't know if there is very cool halo gas, there could be, but it will be very difficult to detect. But we really need to go in the ultraviolet because that's the region where we have all these diagnostic to actually detect this gas. It's in the right energy band of a electromagnetic spectrum to do this study.
Okay. So, okay, here we go. Charles Bell has got a great question for us. It is very topical for the moment of what we're discussing. He's asking, and this is via the Q&A app, what is the mean free path length for these halo gas particles? I.e., what he means by that is the average distance between collisions. Who wants to take that?
Oh.
I will let Chris answer
good questions from our audience.
Yeah.
What's the mean free path? Come on, quick.
Chris is going to calculate it.
You have a napkin or an envelope?
And please do it. And please do it in cal length.
So one of the things we do get information about with the technique that we use is we get information from, because we're looking at absorption of the electrons in the atom go from the ground state to the next excited state, and that should happen a very specific wavelength. And if those patterns, those absorption patterns, show up at slightly different wavelengths, that gives us a measure of how fast the gas is moving, not only with respect to us, but also with respect to the other particles. And so we can get a measure at some level of the temperature, as it were. And the hydrogen atoms at 20,000 Kelvin are probably moving of order 20 kilometers per second, each second, right? So then the question becomes, how far is it to the next atom that you're going to encounter? So I haven't actually done that calculation in my head. They probably tend to be something of order, well, I'm not going to try and do it on the fly here because I'll get it wrong. But it's quite a long distance, actually. And the telling thing about astrophysics...
You do not want to be wrong on the internet.
Yeah.
It will come back.
Yeah.
My kids will correct me if I'm wrong. So, but this is what's really interesting about most gas in interstellar space is that when two atoms collide in space, they can become excited, and we know from just observations that happens relatively seldomly compared with the rate at which they become de-excited. And what that means is that if a particular atom would take thousands of years in its excited state to come back down to normal, it takes a lot longer than that, 1,000 years or so, for the collisions to happen. So I'll just put it that way, at least, that the collision timescales for one atom encountering another are very, very long in these halos.
Cool. Okay, good question, Charles, as always. Thank you. Okay, this one's from Juan Borda. Also, similar question, a little bit different angle. Where are all the gas particles getting their energy? That's a good question. I mean, where does this energy come from? Where are these temperatures coming from? Who wants to take that?
Well, I can take it if you want.
I would love that.
There are a number of, actually there are, as far as we know, there are probably several different ways in which that happens. One is when a galaxy collapses to begin with. That's a conversion of gravitational energy into thermal energy, ultimately. And so that thermal energy heats up the gas and causes the atoms to zip around quite a bit. So it's just like if you drop a brick from a very large height and then put your hand on the bottom of it, it'll be a little warmer than otherwise. The same thing happens with gas particles when they're collapsing into a galaxy. So some of the gas particles that we see in these halos are probably left over from the formation of the galaxy, and so they're heated up gravitationally. At the same time, we know there are a lot of what we call metals, which is everything, to an astronomer, that's everything heavier than helium, right? There are a lot of oxygen and silicon atoms in the halos of galaxies, and especially Andromeda. That's one of the big points of our paper. And those got there because there were supernovae in Andromeda that exploded and pushed these metals out by many hundreds of thousands of light years even. And so the energy for those atoms in part is ultimately tied to the explosion of the supernovae that produced them and then ejected them from the galaxy. So those are some of the ways in which those atoms will get their energy. Also, there's an interaction with radiation just from the background of all the light in the universe that's traveled over billions of years to reach the atoms, they can strip electrons off and add energy into the pool. But there are many, many different ways in which the atoms would get their energy.
So a lot of this could be the result of the... Oh, go ahead. I'm sorry. Go ahead, Nick.
That's asking about where they get their energy, and hence how they get to where they are is, in fact, one of the things that we're very interested in trying to work out.
Okay, good. Okay, so...
I have a question. So you had talked before about the difference in temperatures, that there might be some in a million, blah, blah. So is that stratified in some way, do you think? I mean, you probably don't know for sure, but what do you guess?
Or like, is there a stratosphere and a troposphere?
No,
and that
well, no, I mean, are there different, is there a stratification of the temperature?
We would love to know that. And in fact, the probes that we get the most information from are, they do give you some hint as to their temperature, although we can't always be very precise. And one of the things we're trying to do in the future is map that out, right? Is the colder gas found preferentially closer to the disk? Is it found preferentially along the what we refer to as the minor axis of the galaxy, right, perpendicular to the plane of the galaxy? But we don't know that yet. We have, as Nicholas said, we have 5 targets that are within the sort of 1 million light year sphere of influence of Andromeda.
But as Nicholas said earlier, all galaxies, you believe, have these halos, and so they're kind of like part of they're almost like remnants, it seems to me, of the galaxy's history a bit, right? I mean, this is kind of some residual energy that's kind of hanging around over the galaxy itself, in part. I mean, the other things you said with star formation are also true, right?
Well, they are remnant, but they are not just remnant. They are really an active part of the galaxies, in the sense that you have this massive gas flow in and out of a galaxy. And so it's a very dynamic place. They're just not the remnant of a galaxy formation, but really participate to the evolution of the galaxy itself.
So actually, and that's again one of the big questions we'd like to know. What fraction of all that gas that's in the halo is a remnant from the initial formation of the galaxy? What fraction of it comes from other galaxies that zip by and give up a bunch of their mass? What fraction of it is due to the supernovae blowing up and filling the halo with metal-enriched material? And then again, you know, as the supernovae explode and send a bunch of material out into the halo, some of that eventually will recollapse and form new stars, and we'd like to know what fraction of that stuff that's up there now will eventually fall back down onto the galaxy. So as Nicholas says, it's very dynamic.
Okay. So here's a question from, I can't read this. I can't read this character. It's some characters I can't read, but he's asking, what would it feel like to live inside that? Would it be possible for some civilization to live somewhere inside that kind of halo without even realizing it, considering the low density? I would imagine probably not, right? I mean, we're very rarefied atmospheres.
Yes. No.
Yes. No. Definitely. Okay. So.
Actually, I do have a question from Twitter that we were talking about with its size. Let me pull that up here and screen share it real quick. And this one is from Parrish Patton. And actually, I have a few questions from Twitter, but we'll hit this one first because other ones will be good for later in the show. But how many light years away is a halo that was discovered? So I'm assuming, as far as what's the radius from the galactic center is what I'm assuming that Parrish is saying. So how have we been able to actually measure how large the radius is of this halo from its galactic?
Yeah, because it's in that graphic, but the thing you don't see is the measure of how big the little galaxy is in the center of that graphic. Anyway, go ahead, Chris.
The radius is 1 million. Sorry, the radius is 1 million light years from Andromeda. That's 1 million. Yes.
And the distance from the Milky Way to Andromeda is about 2 million, 2.5.
Right. So it gives some context. I mean, when we're thinking about the size of the galaxy itself, I mean, I know ours is around between 100,000 and 200,000 light years across. When this is 1 million light years, that's obviously dwarfing what we see as the galaxy itself. So this is quite spread out.
But that would suggest that it's possible that the two halos are actually interacting.
Yeah, that's right. That's a
they may soon, and
Okay, well, while we're talking about these two galaxies coming together, I have a question from Richard Snodgrass, who is asking, though Andromeda is on a collision course with the Milky Way, is it not correct that actually none of the heavenly bodies from either galaxy will collide?
So if by that you mean stars in those galaxies, then probably not, actually. This is one of the strange things about astronomy, is that galaxies collide all the time, but stars very, very rarely do, because almost like the air in this room and such, the galaxies are made up of little particles, and there's a lot of space between those particles, right, those stars. Now,
and it may...
having said that, of course, the stars won't collide with each other. They'll just sort of pass right through each other. But the gas in these galaxies, those gaseous halos and eventually the disks, those do collide and interact with each other in a strong way. They form shocks that heat the gas by quite a bit, can trigger a lot more star formation, and hence more supernovae, etc., as that happens. So it will be a fireworks show in that a huge number of new stars will be formed when this collision happens, because the gas clouds will collide rather than the stars.
So is it possible?
Actually, a similar question here from Twitter, and I did pull down an animation for it too because they were asking about it. This is from @Shadow404. Are there any simulations of the Andromeda galaxy colliding with us, and what will happen to our star, sun, and system? And you already touched on that, but I did pull up one of the amazing animations that have been put together through NASA. So let me put this up here to give more of a visual representation of what we're looking at in, what, 5 billion years, something like that?
Yeah, about 4 or 5 billion years, yes.
Although if the halo that you've discovered while this is running is if the halo is 1 million light-year radius away and it's 2.5 million light years from us, and let's assume our Milky Way has a similar halo, they may be interacting pretty soon.
Yeah.
If not already.
Exactly.
Yeah.
That's my point.
When these very outermost edges of the halos collide, it will be a little less than dramatic initially. Because again, the
don't stay up night. Is that what you're
saying? We're going to bump up the density possibly by a factor of 1.5, right?
Right, exactly. And so you might have one particle per 1,000 cubic centimeters.
Yeah, for example. Oh, stifling.
Getting out your UV telescope in the backyard maybe a little premature. Is that it?
That's right.
Yeah.
Okay. So yes, and this is where you were saying you were I think, Nicholas, at the top of the hangout, you were saying something about these halos becoming part of or these galaxies becoming part of an elliptical galaxy.
Yeah, eventually they will merge into an elliptical galaxy. Yes.
That's right. And ellipticals are among the largest and oldest galaxies in the universe, and they tend to be so big because of interactions like this here that we're looking at. So, okay, well that's good.
Too bad.
So Samuel Mitchner on the Q&A app is asking what more can be learned from this halo observations over time. Are you guys going to go back and look at these again?
Yeah.
And if so, what can we learn from these? What do you expect to learn over time?
Well, yeah, we're actually going to look back, and we have just got so as you know, the Hubble just released his announcement of a proposal that we're selected for the next cycle, and so we have a proposal.
I love this theme, Carol. Every hangout.
Woohoo! Are you going to ask more time? Yes, we are. And did you get one? Yes, we did.
Yes, and it did. We did. So.
Congrats.
Hey, you got Hubble time. Awesome.
Yeah.
Congratulations. It's not easy. It's
not, especially because we actually asked for a lot of time and a lot of quasars. So yes, there is a lot of things that we can learn. So with this first project, what we did is really to show the existence of a halo around Andromeda. But because where we have detected the actual halo, we have, as Chris has said, we have only 5 targets within this 1 million light years radius. So now we want to go back with the Hubble, and we have selected quasars not up to 2 million light years around Andromeda, but up to about 1 million light years, meaning behind the halo of Andromeda. And with this project, we truly hope to actually characterize the gas properties of the interaction of the halo with Andromeda. So we have selected targets, especially around the major, minor axis, because these trace different type of phenomena. As Chris was explaining, you have these outflows coming from the galaxies, and they tend to be along the minor axis, while inflows, meaning gas that is feeding the galaxy, is coming more along, or is thought to come more along the major axis of the galaxy. So with this new program, which is 18 quasars, so now we will have a total, I believe, is about, if I got well, the total number is 25 quasars within 1 million years. Yes.
Okay.
Yeah.
Okay, so there you. Well, that feeds into another question I wanted to get to from. Oh, where to go? Here it is. This is also from Charles Bell. He's asking, how many quasars have you used to measure the gas halo for the Andromeda galaxy? For this study, you used 18, but that schematic showed that there were 5 that really gave you good data, correct?
Exactly. So these are the one in the inner region of within the 1 million light years, because that's where we detected the halo of Andromeda. And all the other quasars are beyond 1 million light years, and on most of them except one, we didn't detect any detection of yellow.
But this was important, right? Because this first set of analysis told us that the halo existed, and that it only went out to 1 million light years, which means that we don't have to target a bunch of quasars very, very far out. We can focus on that inner 1 million light years, which is the focus of this new proposal that went in. And so we're moving from demonstrating that the halo existed, which is what we did in this first work, to now actually mapping it spatially and with radius.
Okay. So increase the resolution, so to speak, right?
Exactly.
Yeah, exactly.
Yeah. Okay. Well, good question, Charles. Thank you. But here's a good one from Juan Borda that I'd like to know the answer to as well. So he's asking, does this mean that all observations have to be corrected to adjust for our own halo's absorption? So if our galaxy's halos are starting to interact, do we have to make any corrections, or are you not worrying about that? I mean, I'm sure it's going to be a while before they start interacting, but what do you think? When two halos of two galaxies start interacting, does that make things more complicated?
Perhaps, and in fact, you should encourage him or her to read the paper, because we spent some time trying to assess if that was an issue we had to deal with or not. And in part, again, coming back to the fact that we can measure the Doppler shift of the gas, we can measure how fast it's moving. We know how fast Andromeda is coming toward us at about 250 or so kilometer per second, if I remember correctly. We can focus on the gas that is moving in the way that we expect the halo of Andromeda to move. And so that automatically then excises and removes from the contamination the gas associated with the Milky Way, for example. We know over the velocity spread over which we expect to see that, and so we can ignore that or use it for other purposes.
So why can't we see the Milky Way's halo? Is it because of the stuff that's in between us and the exterior of the galaxy? Is it too diffuse? Why can't?
Well, the problem is, I mean, we probably, using this technique, we're seeing it, but it's hard to separate because it's at the same speed, at the same Doppler shift as gas that we see in the disk of the Milky Way. It's hard to separate whether we're seeing gas in the disk or relatively near the disk within the first, let's say 25,000 light years, and stuff that's much, much further out. And in fact, again, that's the other problem, is we can't talk about the total extent of that gas right now from the Milky Way, because it just gets confused with all the stuff that we see that's very, very nearby. That's much more dense, much more gives rise to much stronger absorption.
Now you might remember, and to that point, you might remember that there were, using quasars, a similar technique was used on the Milky Way to find these bubbles.
Right.
And the only reason that they could find the bubbles,
That's right,
as Chris says, is because of the velocity. And part of the bubble had the same velocity as the galaxy and all the other stuff. So all they could say is, well, there might be stuff there, but it's all mixed with everything else. It was only the stuff that in the bubble that was moving that would tell them that those bubbles were there.
Yeah,
so
I remember that.
That's the same problem.
Kind of had these lobes that came out of the center of the galaxy, right?
Blue and red shifted, and it's for the same reason.
I remember that. Okay. Oh, that's cool. Okay.
Yeah.
So let's see here. Richard Snodgrass is asking, since we don't know exactly what dark or negative energy is it safe to say that we won't know the effect of the galaxies when the halos collide? I think that's getting a little. What do we know about have you been able to study these halos, or has anybody been able to study these halos with interacting galaxies that are already in the process of colliding?
Not a whole lot, and I think that on the dark energy side, we don't know on what scales we expect that to operate, and whether it would have anything to do ultimately with the dynamics of how these things collide. Certainly, in terms of galaxies colliding and their gaseous halos interacting, I'm not aware of a lot of work that's been able to be done on that, although, if I remember correctly, too, there were some approved programs in the next cycle of Hubble to do something like that. So.
Oh, good. So excellent. Well, that's a good point. I mean, dark energy, so little is known about it. It could be that the only effect it has is on the large-scale structure of the universe. We just don't know we don't even know if there's any density changes in dark energy, or if it's the same everywhere you look. So, there's so little is known about that. So, good question. Thank you, Richard. Okay, so what about you, Scott? Am I missing anything? Are there any things in Twitterverse?
I do have a few things from the Twitterverse. One is actually quite relevant to what we were just talking there. So let me pull that back up. So this is at Pensive TM. It says, how do you adjust your measurements for dark matter and energy interactions? So we did just touch on that a little bit. And with especially with dark matter, it tends to be in big clumps of massive things, whereas with the dark energy, we're still figuring a lot of that out. Another one here is, and we touched on it briefly earlier, but this is from at Fine Woman.
She came to us from Periscope.
Yes. So thank you for joining us on Periscope. But were the halos initially theorized, or were you surprised at seeing them?
We know that galaxy, well, as I mentioned earlier, it's part of a process of forming galaxies with halo waveforms. So they've been theorized for a very long time, and but observationally, I think it's only, well, we had some evidence in the Milky Way, but very within 25,000 light years, so very nearby of the Milky Way, that there must be some diffuse gas. But on the large scale that we're observing now, it's only really in the recent years, and that we've been able really to characterize and observe these halos. So it's not really a surprise that we observe them. But we are now at a stage where we can actually learn something, and that's in great part thanks to this UV spectrograph on the Hubble, and that's really a unique wavelength to do this type of study.
So I should say, though, that while the existence of halos was not a surprise, because that traces back to the 50s and 60s even, what has been coming out in the last couple of years that is very exciting and somewhat surprising is that the halos, like we see around Andromeda, contain as much mass as all of the stars in the galaxies that they surround. Yeah. And in fact, contain probably, and also contain as much, as many of the metals as we see in the disks of those galaxies. So we're in terms of all the metals that were ever formed in that galaxy, probably half of them are now outside of the visible disks and residing in the halos. And that was surprising.
Which actually really segues into another Twitter question, and this is from at Barbara_Smile, or Barbara Ann. So, could the halo expand in the future? Is there any evidence to suggest that it would expand, or would be contracting towards Andromeda? Or
these things are incredibly dynamic, and they're always being shaped by the explosions of stars in these galaxies that are pushing on them. They're being shaped by gas that's falling in from the intergalactic medium that is plunging through the halos. They're probably not round and spherical, but they're some lumpy, filamentary, very messy compilation of many processes going on.
Yeah, space is lumpy.
Yeah, exactly. So they could expand, they could contract. There are lots of things they potentially could do, and it's hard really to say. As this galaxy interacts with the Milky Way and those halos come together, some of the gas is probably held up buoyantly, and so we probably expect it to act kind of like our own atmosphere. But if you suddenly took our atmosphere and made it really dense, parts of it would fall to the ground, right? And some of the halo that we see here may do the same for Andromeda. It could fall to the center. It's just hard to say. It depends on the details of the evolution of the galaxy and its interaction with the Milky Way.
Very good.
I want to go back. I'm really puzzled. I'm puzzled by the metals in the halo.
Yeah.
I mean,
So are we.
It can't be exactly the same as the disk because M31 is very metal rich. So there's some difference, but I don't understand.
Talk about what you mean by
where
metals.
it comes from. I don't get it.
By metals, what do you mean, Carol?
Anything heavier than helium.
Right.
Well, that's what we call metals.
I know. I just want to clarify that. It's a weird definition.
Chris said that, but
Yeah,
he
okay.
did give us the definition, and I mean M31 also has globular clusters, and some of them are more metal rich than the ones in our galaxy, and some are not.
Okay.
So I'm not getting it.
So this has actually been a long-standing issue in many ways, in that there's been what astronomers have referred to as a missing metals problem. And the idea was that when we added up all of the stars that we see in the universe and we try to piece together how many silicon atoms or how many oxygen atoms they form and integrate that, and then we look at all the metals in galaxies around us, there weren't enough metals in the stars and the gas inside the disks of galaxies to be consistent with these all the star formation we'd seen previously. And look, those calculations are hard to do, so there are lots of uncertainties.
Exactly.
So maybe you think that is just we just didn't get the calculation right. But now what we're finding, and again this was surprising, is that when you look not only at Andromeda but a lot of other galaxies in the universe, when we started to do surveys with the new ultra-sensitive spectrograph on the Hubble Space Telescope, it seems like the amount of metals that have been ejected from sort of typical galaxies like Andromeda, like the Milky Way, are equal to the amount that have been retained. And you're right, that's incredibly surprising, right? And makes you a little uncomfortable in some ways. But it's
So there was a lot of mixing going on early on. Interesting.
Well, and speaking of metallicity, I mean, one thing that we know is that globular clusters are very tend to be very small in their metallicity. And there's a question here on Twitter. It says, do globular clusters exist in these halos? Now, we were talking about how we're seeing heavier metals coming up there. And again, this ties into my really bad joke. Well, I'll try not to say on air, but it's awesome. It's awesome for the astronerds. But have you guys, is there any evidence for any globular clusters out there? I mean, we're talking about this being millions of light years out there, and the globular clusters are going to be closer to the galaxy itself. Is that correct?
So I think like the halo we're looking at, and Nicola can weigh in on this too. Globulars are certainly more concentrated towards the middle, so their density, let's say, is higher as you go closer into the galaxy. And we would say the same about the halo, that it tends to be higher density in the inner regions, lower density in the outer regions. And so I don't know the most distant globular cluster associated with M31, but they probably have some that are several 100,000 light years out at least. I don't know about 1 million, but that's just because that's not the sort of work I do.
Yeah.
Right.
Yeah.
So can I do my globular cluster joke about metallicity?
Let's just do it. Let's just do it.
Globular clusters are like really, really old, right? And they look at the galaxies, and they're really like the older people in their rocking chairs on the porch saying, "Darn you kids and your heavy metals." And
Oh gosh.
yeah, yes.
I'm sorry. If you ever asked to give that talk
You're
joke
welcome.
again, the answer is
I'm
no.
just waiting for it to end. Has it happened yet? Has the joke happened? Oh, it already happened. Oh, I missed it. Okay.
No.
All right.
No.
Well, Chris, I have one final question for you as we get ready to do this. You have on your board back there, Hi Hubble fans.
Yeah.
I got to ask you though, would you now consider yourself, now that you've gotten proposals approved twice, are you a Hubble hugger now, or are you a Hubbler?
I think it would be a Hubbler.
Are you a Hubbler or a Hubble hugger?
I've been using Hubble for almost 20 years now, so I think I definitely fit in that category.
Yeah.
Of which one? You got to. We're not letting you go.
What's the definition of Hubble hugger and Hubbler?
Well, there was a discussion of shutting it down a long time ago, and
that's Hubble hugger.
And
it's like Trekker versus Trekkie. It's starting to become a thing. Hubbler, Hubble hugger. I'm telling you.
Well, we spoke earlier about Hubladors, right? So.
I'm so glad you brought that up. That's my favorite still.
I'm in the Hubbler camp.
Hubbler, I know.
Hubbler?
I'm in the Hubbler camp.
Yeah, and I'm a Hubble hugger. Okay, so anyway, Carol is she's just Hubble. She's just
like,
all,
you guys are
all over it. Yeah, she's like, I'm not even playing. She won't even play. We forgot to do our drinking game, but the word of the day was.
Hey, I've been doing it.
I know. The word of the day was Halo, and it's over now.
Yeah, the drinking
all right.
game was
Well,
Halo.
we have to catch up, so.
Yeah.
Halo.
My Einstein hug. And
okay. My mistake. My mistake. I want to thank everybody who joined us from Periscope. I did an experiment with that before we started up. Periscope is a Twitter live streaming app which I've just been playing with and seeing if it's fun. I gave you guys a behind-the-scenes look at setting up a Hubble Hangout today. Leave us comments in the Hubble Hangout hashtag for any other ideas you may have for using Periscope, and we'll try to do it. We had a lot of good viewers, a lot of good interaction from comments from that, so I want to thank you for joining us in the Hubble Hangout later. So that's good. On behalf of our guests, I want to thank Nicholas Lenner and Chris Hoke from joining us. Thank you guys. This has been a great hangout. Thank you so much.
It's been a lot of fun. Thank you.
And when you get your next set of observations, are we going to have you going to come back?
Absolutely.
I hope so, yes.
Better.
Carol's answering for you. She's
You're
coming back.
I have influence. Now I can say, don't give them their time unless they.
That's right. That's going to be a good thing for the TAC. Are you willing to do a Hubble Hangout?
The checkbox.
Boy, our calendar will fill up in no time.
Yeah, all right. It will be really popular.
All right, Hubble huggers, Hubblers, Hublandos, and all the other things that you guys are in affectionate Hubble land. I want to thank you guys for watching. Remember, speaking of our schedule, this is Pluto month, so we're going to be stepping aside next week. We will rejoin you in 2 weeks, where I think we might be talking about WASP 33b, but we might be doing something else. We're still working out the details on the schedule. So stay tuned. Follow us on @Hubble Telescope. Also do that on Periscope as well. You'll learn about these hangouts that way. Subscribe to our YouTube channel, Hubble Site Channel, and follow us on Facebook @Hubble Telescope. So
and we're now also on Instagram. We are @official Hubble. So @official Hubble. We are on Instagram. It's we started up silently. We didn't let anybody know it is loaded. And so we're
already at 1,400 followers. It's nice.
We love interacting with you guys. So please follow us over on Instagram. We are @official Hubble, and we are putting up lots of amazing things on there. So please follow.
Okay.
Yes. So we'll see you guys in 2 weeks. Have fun with Pluto. Let me know. Take pictures of your Pluto Palooza. I want to see what those
I'll see what I can get together with my planetary friends at JPL.
I'm depending on you, Scott. I need to see it. Okay.
All right. Let us know what you do. Okay.
All right, folks. Thank you all for watching, and as always,
keep looking up. So, I mean, as sure many of you know, on Twitter, you might have seen us on Periscope earlier in our, I guess,
yay, Periscope people, that was fun.
And I'm sure we'll be incorporating more of that later on. But speaking of Twitter, you can engage with us on Twitter using the hashtag Hubble Hangout. Also, please follow us @Hubble Telescope, and I will be tweeting out pictures and stuff like that throughout this Hangout. If you have questions for us, please use that hashtag, because I will be able to see them and post them up here. Also, since we are broadcasting live on Google Plus and YouTube, you can interact with the Q&A app, which is on both of those. I just posted on Facebook as well into our event that we're live. You can click on the YouTube link, and it will give you another option. Say, we're answering your questions. You can ask your questions. They can be upvoted by other members of the community, and when we see them, we can select them and answer them live on air. And then also just regular commenting. So you can comment on the YouTube page itself, on the Google Plus page, and I'll try to keep an eye as well on anything on our Facebook event as well. So all the internets are being watched. and please, like, try to keep them in one place. It makes my job easier, but I will be an octopus and reach out everywhere.
Yes, we will try to capture you as much as we can. So the Carol, somehow you got cloned. There's two of you.
Yeah, I did.
Okay.
I don't know what's going on.
All right, so let's get to the topic of today's hangout. As I mentioned earlier, scientists have been using Hubble for a variety of ways, and one of the ways in which they've been using it recently is they've been looking at the Andromeda galaxy, one of the nearest galaxies to us. It is a spiral galaxy much like our own. It's also heading straight for us. It's about 2.5 million light years away. And joining me to talk about their observations is Dr. Nicholas Lehner from from Notre Dame or Notre Dame, whichever way you want to put it. Welcome, Nicholas. It's good to see you. Also with us, Chris Hoke also from Notre Dame. The sun would look like from Pluto at that particular time. So it's called Pluto time, and there's also a link to that. So, and finally, they have videos every day. They're broadcasting a new video on Pluto every day. The link to that is also in the description box. So it is going to be a Pluto extravaganza. I like that better than Palooza. This coming month. So by all means do it. In fact, it's so much so that I think we're going to be taking a bow out next week and letting all the Pluto events happen. So there won't be a hangout next week either. Okay.
Although, to be fair, I'm sure I will be tweeting from Hubble of our images of Pluto and celebrating and like, yay, go New York.
Yeah, I've been following you on Instagram. You've been doing a lot of things with Hubble too. You've been going different places with Hubble. I've been following you on Instagram. I've been watching you.
So I have a hashtag called Hubble in me. A few weeks ago, I went to the Endeavor exhibit here at the California Science Center, and I found this awesome little space shuttle that had a Hubble Space Telescope in it. So I hacked it and removed it, and I take it everywhere I go and take selfies.
Oh, you voided the warranty.
If you want to follow the hashtag Hubble in me, you will see the silliness that I get up to. My last one was when I was rock climbing and then had ramen afterwards. And
yeah, that actually looked pretty good. I wish there was a good ramen place near me. Okay, so all right, let's get to today's hangout. Speaking of hashtags and social media, we're going to tell you how you can interact with us during this hangout in just a minute. But let me welcome my good friend Carol Christian, who I don't know if you can adjust your camera a little, but you're being eaten by your lower third there. Hi, Carol. Dr. Carol Christian. She's the outreach scientist for the Hubble Space. There you go. Thank you. Welcome back. Hello. And also
I'm
joining
not
me.
back. I'm still here.
you're still here.
She never left. She's still part of the last hangout. She just stayed there and sat there. We forgot.
Absolutely. Absolutely.
Oh my gosh. All right, and Scott Lewis, he is our internet driver extraordinaire. Hi, Scott. Why don't you tell everybody watching how they can interact with us during this hangout? Because we want your questions and comments.
Absolutely.
They are here both to discuss their observations. So, Nicholas, let me start with you. Why don't you tell us a little bit about these galactic halos? Before we get to your observations, I want to take a step back and say, what are these things? Are these, you know, when I think of halo, I'm obviously thinking of one that I always have over my head because, you know, I always have one of those. But, you know, what do you think about? Give us some idea of what these are, these halos.
Well, the halos that we are. Do you hear me? Yes.
Yep, loud and clear.
Yes. Sorry. So the halos that we're looking at is are gaseous halos. That means it's gas. It's not these dark matter halos that we can look. So that's the first thing I would say. And they are basically, we think, they have been formed at the same time that galaxies, and they are completely part of this process of galaxy formation. And so, the shape of these halos, they can be. We think they are basically, they could be spherical around the galaxies, for their shapes are not very well constrained right now. So all the galaxies, we think that all the galaxies in the universe have halos.
Say that again. All the galaxies.
All the galaxies in the universe have some kind of halos, and
regardless of their type, regardless of what they are.
Regardless of the type, and they can be, and depending on the mass of a galaxy, this halo can also have different masses.
So we have one, the Milky Way then.
So the Milky Way is most likely one. We know that we actually have some evidence that the Milky Way has some halo. The problem living in the Milky Way is that we don't know, we can't really know its extent because we don't have background sources far away enough that tells us the scale of the Milky Way halo, which we can actually do with M31 and Andromeda.
They're just audio only. There's the one on comets. Could comets have brought life to Earth? That one's the first one. That starts at noon, and then going all the way through 3 o'clock. So an afternoon of Q&A, and there's the dwarf planets one. What worlds lie beyond the giant gas giants? Oh, and this icy moon was good too. Do habitable worlds exist beyond Earth? So I highly recommend you check those out. If you've got any questions, you want to interact with scientists who think about these things all day long, then that is your chance. Tomorrow, Friday, July 10th, starting at noon Eastern Time and going all the way through to 3 o'clock Eastern Time with the last one. So there is, in addition to the Pluto stuff going on next week, I can't believe I'm saying this, but there is a thing you can do this month, folks. If you're a real fan of Pluto, and I mean a real fan of Pluto, you can start and host your own Pluto Palooza. That's right. There is a way to do that, and there's a link also to that in the description box. They gave I guess this is done by the Johns Hopkins Applied Physics Lab. They've put together a bunch of materials to help you host your own Pluto Palooza. Are you going to do one, Scott? You can do it anytime this month.
We'll see how things turn out. It's very possible. I have many wonderful, nerdy, planetary friends out here in Pasadena, so I'm sure we can find something to do.
Okay, well, make sure you post about it on your Twitter account, and people will show up at your house.
It'll be up on Twitter and Instagram. It'll be everywhere.
I'll be honest, I'm not sure what you do at a Pluto Palooza, but there's a bunch of materials there to help you do whatever that is. Also, as I mentioned coming up, there's a thing called Pluto Time, which is an app that NASA has developed that lets you simulate, or at least try to get a glimpse of what it's like on Pluto, both in the evening and morning hours. It'll calculate for you exactly where on the planet based on where you are on the planet, it will calculate what. Hello everybody, and welcome to another Hubble Hangout. This week we've got another great hangout planned for you. My name is Tony Darnell. I work at the Space Telescope Science Institute. And astronomers using the Hubble Space Telescope have looked at the Andromeda galaxy, and they have found a halo. Not just any halo, but a giant halo. And we're going to talk about what that is, what it looks like, and how they did it in just a little bit. But before I get started, I have some announcements to make. I have a lot of announcements this week because there's a lot going on, as you probably already know. And if you care about dwarf planets, which I guess a lot of people do, then you are going to be in for a lot of fun this month because it is Pluto month. The New Horizons spacecraft is on its way, and next week will be the big week. July 14th is the scheduled day, and if you care about looking at and following all of the things, my best advice to you would be just to watch NASA TV, because all week long they're going to be doing things with New Horizons and things like that. Also, this is NASA's Small Worlds Week, and if you are interested in all kinds of different things having to do with small worlds, then tomorrow, starting at noon Eastern Time, they're going to have a series of Q&As. They're going to be looking at dwarf planets late in the afternoon. They're also going to be looking at having discussions on comets, like was it possible that life was brought to Earth from another comet? They're also going to be looking at asteroids. There going to be Q&As on asteroids? Is there a possibility for any of them hitting us, for example? Things like that. So this is NASA's Small World Week, and I think there we go. She's cycling through them now. There's the one on asteroids. That's at 1 o'clock Eastern Time. And the way you get there is you go to sunearthday.nasa.gov. I've got the link in the description box below. So that's when all of them will be. And I think these are